Hello, I'm Sam Coy, and today I'm going to talk about deterministic massively parallel connectivity. This is joint work with my supervisor, Artur. First, I'm going to give an overview of the results we're going to be talking about. Our main result is a deterministic connectivity algorithm that uses optimal global space and has round complexity equal to the current state of the art. We also provide a conditional lower bound for the connectivity problem. We show that it requires big omega of log of the diameter rounds, unless a very popular and widely believed conjecture turns out to be false. So now I'm going to explain the model and give us all the context we need to understand these results. MPC, massively parallel computation, is a modern model of parallel computation. It's similar in some ways to earlier models such as BSP, bulk synchronous parallel, and PRAM. And in particular, this model has strong connections to distributed computing models like local, congested clique, etc. It's a good model for modern parallel programming frameworks like MapReduce, Hadoop, Dryad, that sort of thing. Okay, so that's what the model is. How does it work? Well, we have M machines. Each machine has S local storage. S is not enough space to store the input. Our input is initially distributed arbitrarily among these machines. Computation, as it does in many distributed and parallel models, takes place in synchronous rounds. So each round, machines receive the messages they were sent in the previous round. They do some local computation on their local data, and then they send some messages to other machines. A machine may only send and receive S words per round. S is its local space. And of course, it also may only store S words per round as well. Okay, so there are plenty of choices we can make about this model, plenty of parameters that we can set, and one of them is the local space that each machine has. There are three sort of main regimes here. There's the superlinear regime where you have n to the 1 plus delta space per machine. So, for example, that's enough local space to store all of the neighbors of n to the delta nodes. There's the linear regime, which is similar to the congested clique model of distributed computing. And then there's the most challenging regime, which is the sublinear regime, where you only have big O of n to delta words per machine. And we're going to be focusing on the most challenging regime, the sublinear regime, today. So with sublinear local space, you can still do a lot of things in MPC. It's quite a powerful model. You can sort n values, you can calculate the prefix sum of n values, you can perform this sort of colored summation. So if you're given n values each with an associated color, we can sum all of the red values, all the blue values, etc. We can also do broadcasts very quickly. We can broadcast values to all machines. Another parameter we can set in MPC is the global space, which is the total space available to all the machines. So the total space available to the MPC is obviously the local space times the number of machines. There are also some common regimes here. We can have polynomial global space, which is quite loose. We can have slightly superlinear global space, or we can have tight amounts of sublinear global space. And again, it's this last regime where we have exactly enough global space to store all of our input, which we're going to be focusing on today. Okay, so let's introduce the problem now. The problem is connectivity. So this is a standard problem in graph theory, but I'll go through it anyway. We want to compute a labeling such that if two of our vertices are in the same component, they have the same labels, and if they're in different components, they have different labels. So for example, this would be an appropriate labeling for the above graph. We're going to have the range of this function be vertices, so we can think of this as sort of picking a representative for each component. So say one of these vertices in the left component is actually called 2, and we're going to pick that as sort of a leader. This is a fundamental subroutine in graph algorithms. It's used as a building block in lots of different things. Now, connectivity in the MPC model depends on what you have picked as your local space. In the superlinear regime, this was discovered to be able to be done in constant time in 2011 by Lattanzi et al. In linear local space, the results are more recent. Jajinsky and Novitsky came up with a randomized constant time algorithm for connectivity in 2018, and this was subsequently improved by Novitsky to also extend to be a deterministic algorithm. In the sublinear regime, though, we have a very different story. There's nothing unconditionally better than big O of log n, and that's from a PRAM algorithm. And the problem seems to be hard when local space is big O of n to delta. And people have noticed that this problem is difficult. And in fact, we have a result which encapsulates that. This is the widely believed conjecture I was talking about earlier. It's the 1 versus 2 cycles conjecture. So many people believe that distinguishing one cycle from two cycles requires big omega of log n rounds in MPC when we have sublinear local space. This conjecture really is widely believed, and we even believe some people even believe that it holds when you have polynomial global space as well. So the local space is really the problem here. This conjecture is often used as a condition for lower bounds. And the reason it's often used as a condition for lower bounds is that actually it's very hard to get unconditional lower bounds in this model. A very celebrated result of Roughgarden, Vasilevitsky, and Wang in 2016 says that any non-trivial lower bounds in sublinear MPC implies that we have a collapse of some complexity classes. This is a slightly informal way of stating the result, but it's a big obstacle for proving lower bounds in MPC. So we often use this 1 versus 2 cycles conjecture as a condition for hardness in this model. Okay, so we can't do unconditionally better than big omega of log n, but can we do conditionally better than omega of log n? Well, there is a trivial big O of the diameter algorithm, right? If you broadcast the highest ID that you've heard about to all of your neighbors, and you continue to do this for d steps, then eventually every node will know the highest ID in its component. So if the diameter is sublogarithmic, we can already do better. But can we do even better than that? Well, okay, imagine we were to continually square the adjacency matrix of our graph. So we connect every vertex to its 2-hop neighborhood, and we repeatedly do this. This would also connect every vertex to all other vertices in its connected component. And it would do so in log diameter rounds, but we need a lot of global space to do it. We might not need big omega of n cubed, as I've written here. Actually, we may be able to do something faster with fast matrix multiplication, but we'd still need big omega of n squared, certainly. The question we really want to answer here is, can we solve connectivity in log of the diameter rounds when the amount of global space at our disposal is just linear? It turns out that we can, and I'm going to explain the ideas behind the previous connectivity algorithms before I then go on to explain how we de-randomize them. So an idea that was discovered by Andoni et al. In 2018 was that we can do this graph exponentiation, this squaring of the adjacency matrix, but we want to stop before we exceed our global space budget. So we only want to do this while we have linear global space at most. One way we can do this is increase the degree of all nodes to m over n. If we do that, we obviously only need big O of m extra edges, and that's fine, because that still fits within our global space budget. And this also takes log d rounds in the worst case. So that's how we add extra edges between vertices in the same component. But okay, what now? We've hit our global space budget. What else can we do? Well, here's the second part of the idea. A graph with minimum degree d has a dominating set of size big O of n over d. So for example, the graph above is n is 10, d is 3, and we've got a dominating set of that size. And we can easily find it using randomization in constant number of rounds. Informally, we flip a coin with probability 1 over d of landing heads, and we add vertices to the dominating set with that probability. We need some extra log factors to get concentration bounds, but this is fine. So an idea is that we can find a dominating set once we have increased our minimum degree, and we can contract vertices that aren't in that set to vertices that are. So with the above graph, if we contract the vertices that aren't in the dominating set to neighboring vertices that are, we'll end up with a path of length 3. And we've already got much fewer vertices. So you may be able to see where this is going. I'm going to explain it. So the outline of their algorithm is then as follows. So we start by increasing the minimum degree to b equals m over n. And then we can find our leader set of size n over b. We can contract non-leaders into leaders. And now we have n over b vertices, or big O of n over b vertices, which means that the amount of total global space we have per vertex has increased to b squared. Because the total space has increased to b squared per vertex, well, now we can afford to increase the minimum degree to b squared. And now we can find a leader set of size n over b cubed. Now, the reason it's not n over b squared is because we also have n over b vertices, and each has degree b squared. And we can contract the non-leaders into leaders. And now we have n over b cubed vertices, and now we have b to the 4 space per vertex. And we can keep continuing this, increase the minimum degree to b to 4, find a leader set of size, big O of n over b to the 7, and we can see here that we're making double exponential progress on the amount of space that we have available per vertex. And since each phase takes big O of log D rounds, we end up with an algorithm that takes log D times log n rounds. Now, there are a few extra details here, which I'll go over. So we have this base m over n for reasons that I'm not going to go into. We also have a slightly stronger result that says with more global space, we can actually do this much faster. An intuitive reason as to why is that we don't have to start at m over n. We can start at, say, if we start at n to the 0.1, we can get there much faster. We can increase b to n much faster. Okay, now there are some problems with this result. The previous result has low success probability, so it only succeeds with good probability in the worst case. The average degree can initially be constant. M over n can be a constant at first. But for concentration bounds for the dominating set algorithm to hold, we need m over n to be some polylog, right? So the idea here is that we can perform some random contractions before we start the algorithm to reduce the vertices by a constant factor in a constant number of rounds. If we repeat this log n times, we reduce the number of vertices from n to n over polylog. And this gives us the concentration bound that we need. An important thing to note here is that we require randomization to do this reduction of vertices by a constant factor in constant number of rounds. I'm not going to go into the details of this procedure, but essentially it boils down to finding a linear matching on a line. Okay, so we have a long path and we need to find a linear size matching on it. It could even be very small. It could be, 1/100th of the vertices that we match, but we need to find a linear size match. And this requires randomness. The other improvement I should mention that this paper made is that, by Benazad et al., is that we can improve the running time by interleaving this expansion and contraction process per vertex. And things get very complicated here, so I will omit the details. But a randomized leader selection subroutine, so this dominating set algorithm, is still used, so we still need to deal with this. And so they improve the result. They improve the result to log D plus log n rounds, and they make the probability high. They also provide a conditional lower bound. The conditional lower bound is the same as ours in that it's big omega of log D, but theirs only holds when the diameter is at least logged the power of 1 plus some row of n. And our contribution to this bound is that we extend it to all values of D. So there are two randomized elements of the connectivity algorithms that we've seen so far. Okay. So this dominating set of size n over D, we need randomness to solve this. It's very efficient to solve this, but we do need some randomness. And also we need to solve large constant fraction matching on a line in order to get this reduction of vertices by a factor of polylog so that we get these concentration bounds. Now the question is, can we make those subroutines deterministic? And the answer, spoilers, is yes. So these are our results again. So we can solve connectivity deterministically in exactly the same bounds as the algorithm that I've just shown you. And with more global space, again, we can solve connectivity in log D rounds deterministically. As I've said, we also improve this conditional lower bound so that it holds for all values of D. And also there are some implications for related problems. So in this paper by Andoni et al., they also came up with algorithms for spanning forest, minimum spanning tree, and bottleneck spanning tree. These use connectivity as a sort of black box subroutine. And since connectivity was the only randomized subroutine in their algorithms, we can de-randomize them again with no asymptotic loss in space or time. So we also get de-randomized minimum spanning tree, spanning forest, bottleneck spanning tree as corollaries of our result. Let's have a look at one of the techniques that we use to de-randomize the connectivity problem. So this is the method of conditional expectations. The idea is that we can think of a randomized algorithm as uniquely determined by a certain seed. In the method of conditional expectations, we want to find a seed that will solve our problem for us. We're going to use one observation repeatedly here. So if a set of seeds meets our objective when we pick one uniformly at random in expectation, then at least one seed meets that objective. So the idea here is we're going to start off with a set of random seeds, and we're going to continuously refine this set such that the expectation relative to some objective function stays the same or gets better. And eventually, when we keep refining this down, we'll end up with a seed that solves our problem. We're going to use the notion of k-wise independence here. And these definitions are quite standard, so I'll leave them up on the slide while I talk over it. In particular, we're going to use k-wise independent hash functions. So the idea here is that we can deterministically construct a family of k-wise independent hash functions, such that choosing a uniformly random hash function only takes log n random bits and produces a k-wise independent variable. So yeah, the fact that we can specify such a hash function using a very small number of bits is very important here, and we're going to make use of this. Okay, so what exactly are we going to do? So given an algorithm which solves the problem that we want to solve using k-wise independent random variables, we want to construct one of these families of hash functions, and remember that we can specify it using a big O of log n bits. Now we want to define some objective function and argue that in expectation its value is sufficient to solve the problem. Now we have to be a bit careful when we define this objective function. The broad idea of what we're going to do here is we're going to split the input among our machines, and we're going to use these machines to test particular random seeds. We want machines to be able to do this very efficiently. So ideally, we want a machine to be able to evaluate this objective function with no communication. So it can't be based on, for example, a very large neighborhood of a node, because we simply don't have room to collect a large neighborhood on a single machine. So we want these objective functions to be locally evaluable. In fact, selecting this objective function is one of the difficult things about de-randomization in MPC. Okay, so how do we actually go about fixing this seed? So we're going to fix the seed log n bits at a time. In expectation, a hash function selected from our family uniformly at random solves that problem, as we've said, right? So we've got this family of k-wise independent hash functions. If we select one uniformly at random, it's likely to solve our problem. In expectation, it solves that problem. Which means that if we consider all the different log n length prefixes of the random seed, there must be one such prefix such that the set of seeds with that prefix solves our problem in expectation as well. This is the method of conditional expectations. So we're going to find a prefix that increases the expectation or has it stay the same, and we're going to iteratively set log n bits of this prefix until our entire seed is specified. And then we have a seed that works. As I mentioned, the seeds are big O of log n in length. We want to fix log n bits at a time, so this is going to take a constant number of stages, and we're going to be able to do it very fast. Here's in particular how it works. So imagine we've fixed the first k bits of our random seed. We consider all possible settings of the next log n bits. All of the machines in parallel and without communication will compute the expected value of the hash functions prefixed by B1 through BK, and then all possible settings of the next log n bits. So each machine will have an idea locally about what it considers to be the relative value of these possible settings. We're going to aggregate, we're going to sum the values of all of these settings over all of the machines, and we're going to pick the best possible setting of the next log n bits of the prefix of the seed. Now, that's a brief overview about how the method of conditional expectations works in MPC. I want to talk a little bit about what we need K to be. So for one of our problems, pairwise independence works. This is finding a large constant fraction matching on a line. And this makes sense if you think about it, right? So you have an edge, and it only really cares if it's being part of the matching or not. And that only depends on the edges that neighbor it. And on a line, there are only two neighboring edges. So pairwise independence suffices to solve that problem. For this dominating set problem, though, pairwise independence doesn't cut it, and we couldn't figure out a way to do this with less than log n-wise independence. This family of hash functions, though, is too large. So there's a formula for the size of the hash family of hash functions, and with log n-wise independence, we, I think, get something like log squared n bits specifying each hash function, and that's not going to work. We need to solve this in constant rounds. We can only set log n bits at a time, so this won't work for us. Our solution here was a technical tool called k-wise epsilon approximate independence. So the idea is we have some weaker tail bounds because our random variables are no longer perfectly k-wise independence. There's some noise, so we get weaker tail bounds. But this family of hash functions is smaller again, and in particular, we can specify our hash functions if we set our variables particularly carefully with log n bits, or big O of log n bits, and again, we can then use the method that we've just seen to solve the problem. Now, I want to end the talk by talking about component stability. So Ghaffari, Kuhn, and Wito in 2019 proposed a new framework of conditional lower bounds for MPC. So the idea is this: if a problem has a big omega of t lower bound in the local model of distributed computing, then all component stable algorithms in sublinear MPC require log of that. I'm not going to go into the details of why this is the case. but I'm going to explain what component stability means. If formally, component stable means that vertices in different connected components have independent outputs, so they don't affect each other. This is a very reasonable assumption in distributed computing, because in distributed computing, you often have nodes only able to communicate if they have an edge between them. But in MPC, it turns out to not be well motivated all of the time. And the method of conditional expectations is not component stable. The reason it's not component stable is that the vertices on our graph all participate in the setting of the seed. The machines of all vertices will evaluate the quality of each seed. And so a machine's evaluation in a different connected component can affect a vertex in another connected component, because all of the machines jointly set the seed. There's no sort of independence between components here. And in fact, because of these component stability lower bounds, our de-randomization results would both be impossible if we restricted ourselves to them. Okay, finally, I want to end the talk with some open questions. So we still have this plus log n at the end of the complexity for the connectivity algorithm. That's there in the randomized case, and of course, it's also there in the deterministic case. A major open question is, can we get rid of that log n? Can we solve the connectivity problem with sublinear local space and optimal global space in log of the diameter rounds? Another question is, under what circumstances does disregarding component stable algorithms and choosing an algorithm that's component non-stable, component unstable, lead to faster algorithms? It seems to be very useful for de-randomization in particular, but under what other circumstances is it useful? And finally, can we obtain faster algorithms for MST with optimal global space? So currently with optimal global space, the current state of the art is log n rounds, and that's from a PRAM algorithm. When we have more global space, we can do much better. We can do big O of log of the diameter of an MST. But improving the bound for optimal global space is very much still an interesting open question. Thank you very much for listening to my talk.